Hi everyone, welcome back to another exciting tutorial on OpenSees. Uniaxial material models are very fundamental to finite element analysis on OpenSees. Thoroughly understanding them in detail is a very challenging job because the documented literature on these constitutive models is very limited and in many cases there is no documentation. Over my experience, I have learned that one of the best ways to deal with this challenge is to learn to study the source code itself. In this tutorial, you will learn a simple technique to study the source code corresponding to the uniaxial material models. Don't worry, we are not going to jump into the ocean of OpenSea source code. That's really huge to handle. What we are going to do is we will separate the C++ source code snippets corresponding to the particular material model, for example, steel 01 or concrete 01 or concrete 02, etc. And we will study them in detail. In this particular tutorial, we will explain the step-by-step process to extract these code snippets from the full repository and compile them independently and study them line by line. I'll keep this tutorial as simple as possible. If you get any questions, please write them in the comment section. We are happy to discuss and share our expertise. Before we dive deep into today's tutorial, I have a small request. We put a lot of effort for creating this informative and engaging tutorials for you. If you like our content, please subscribe to our channel. Your subscription is very valuable to us and it really motivates us to create more tutorials like this. Let's dive into today's tutorial. Today's tutorial requires the installation of two softwares. One is Visual Studio Community Edition and the second one is Armadillo C++ library. The first one, Visual Studio Community Edition, you can download it from here. It's free to download. The process of installation is clearly explained in one of my old videos on source code compilation. In this tutorial, I have explained the installation of many softwares like Intel Photon Compiler, ActiveTCL, Anaconda, OpenSea source code, etc. You don't need all of these things. You just have to install the first one, Visual Studio 2022 edition. That's it. The second one is Armadillo library. This Armadillo is a user-friendly library for linear algebra operations, just like NumPy of Python. You will have functions to deal with vectors, matrices, and to perform some operations like file reading, file saving process, files in the sense you can deal with text files, CSV files, Excel files, etc. One big advantage of using Armadillo library is the syntax of these Armadillo functions are very similar to the syntax of MATLAB. The developers of this library intentionally made this decision, so you will always feel like you are using MATLAB in C++. That's one of the biggest advantage. I really like using this library in OpenSea source code, and this is open source, so it's free to download and free to work on. This is the documentation for this library, so don't bother about it. We will explore it in detail. Here you will see this download button. There, whatever the stable version that is displayed on this website, just download that stable version. So just click this link. A new link will be opened and just save it somewhere in your local. Just that's it. So it is saved in my local desktop, another folder I have created in test. So just extract this. It is extracted here. Yeah, just like this. So let's keep it for a moment. I have already installed this Visual Studio 2019 version in my machine. So you can use this 2019 or 2022 version, it doesn't matter. So right now I'm opening this 2019 version. So what you have to do is just create a new project, select C++ here and select Windows platform here and keep all projects. Here select an empty project, that is very important, and click next. Type the project name here, Uniaxial material models. So just in short notation, I'm just putting uniaxial MMs. MM represents material models. Just I'm saving it somewhere in my local repository. So in this constitutive model, I'm just creating a new directory, T6 uniaxial MMs. So I'm saving this project in this particular directory and just create here this header files, resource files, source files. These are all some filters that you will get by default when you started a new project. You don't need these things, so just delete, because create new filters as per our need. So after that you need some files here. For now let's deal with simple steel 01 for time being. After that we will explore the other material models, concrete 01, concrete 02, concrete CM, etc. Steel 01 cpp github. This is the GitHub. So just go to this repository. So this is the main file. So what you need is you need this cpp file and steel01.h header files. So what you have to do is you just download this and save it in the directory where we just created our project, that is Uniaxial MMs, and within that you will see another Uniaxial MMs directory. Just save it here. Similarly, save this also in the same directory. I'm adding those two downloaded files into this project. So open this add existing item and bring those two files .cpp and .h into this. That's it. And after that, if you look at this header file, we have many things written on this header file because this header file is a part of another source code OpenSees. So we have many dependencies. So when we are dealing this particular material model separately, we don't need all those dependencies. You can comment out this one. Shortcut is Control plus K plus C. So after that, you can simply neglect this public Uniaxial material, and then we can remove this tag, not necessary, and then all these things are not necessary. Similarly here, get energy, get sensitivity, get initial tangent, get stress sensitivity, all these parameters are also optional, not necessary when you are dealing this as a separate file, and these properties are very important. This also not necessary, this also not necessary. We make these changes in this header file, and similarly within the .cpp file we are going to make some changes. Here these things are not necessary, just comment out these things: string, parameter, information, matrix, vector, all these things are not necessary, just comment out these things. So we are just having steel01.header file, math.h and float.h, and after that this function is not necessary. Basically you have disabled certain functions and certain calls to some header routines in this header files, in this steel01.h header file. So when you make those changes in the header file, within the .cpp file you will see some errors, and those things are highlighted in this red color. So you just have to go to this red color and just comment out those lines actually. So here it is stating like include steel01 file is not available. So this is there in this project, but somehow this project is not able to find it. So what you have to do is you just have to change the properties, like you just have to add the directory to include that file. So here just click this folder icon and just select this Uniaxial material properties. This is the location where this steels 01.cpp and the steel01.h files are available. Just select this folder and click it, press apply. See, it went off. And now just go to this red color, all this cmax, cstrain, these are not showing because we have a tag that is different. So we don't need that one, and we don't need this uniaxial material also, just like that, and we don't need this energy also. Those terms are also not necessary, just uncomment out them. So just these are also not necessary in the steel01, and just comment out them, and then this whole function is not necessary in the destructor. So these are called constructors. Constructors basically initializes the variables defined in this steel01.h. Here we have defined so many variables, private variables. So we need some process to initialize these values. So that is what we are doing in this constructor. And destructor generally represents just like constructor initializes the variable, destructor deletes that particular object. So we don't need that. We deleted it. Similarly, we came here and since we are not dealing with any energy related terms, I'm just turning this off, and this one here, this one is also not necessary, and this uniaxial get copy not necessary, and send self also not necessary, receive self also not necessary, print is also not necessary. We have deleted that function in the header file. Just press Ctrl K C and just set parameter KC, update parameter, activate parameter, get stress sensitivity, gradient, get initial tangent sensitivity, commit sensitivity. Those are also not necessary. So I have commented out all these things. So that's it. These are the changes that we need to make in this Steel CPP and Steel01.h. Let's see if we can build this library. So let's click this build solution. So you see we have got two errors. One is external symbol underscore main reference in project is missing actually. So we need to create one main function to access this function. So I have created that already before. Just I'm going to access that CPP file for you. So this one. So this file has a dependency on this strain history.txt. We need these two files. So I'm just copying those two and then pasting it in our repository. Pasting it here. So now I'm adding that CPP file to this existing just simulate steel behavior.cpp. So this is the main function that I have written. So this function uses Armadillo library. So we have to link the downloaded Armadillo library to this project. So where is it? Click this C++ general include directories. So click edit and then add a new directory. Just click it. So you just have to go to the location and then this include library, just include library, click it, press OK, press OK. That's it. So all of these errors and warnings gone. So this is our main function. Let's build it. I will come to this main function in a minute, but let's see first if this main function is working fine or not. Let's rebuild the solution. Rebuild does both cleaning and building it again. Yeah, that's it. So our project is succeeded. We don't have any errors in this project. So we can use this. What I have written in this main function is I have called a steel01.h file and armadillo include file into this. So here using I have created one vector called strain history of type dvec. Dvec is a vector type just like integer, double precision, such kind of variables in C++. Dvec is a data type of Armadillo library that corresponds to defining vectors. Vectors are one-dimensional vectors, and here we have another data type called dmat. Dmat generally used to create matrices, two-dimensional or three-dimensional, any dimensional matrices. And uword. Uword is similar to integer type of C++. When you want to create integers in C++ using Armadillo library, you have to use uword to create this unsigned integers. So what I did is I have created this strain history.txt before. So this is the strain history that I am going to supply to this source code, and then I have created a few variables for managing this vector and matrices. So mat size that defines the size of this all the arrays that we are going to create. So this is the stress history. This stress history corresponds to the strain history, and this stress history we are going to evaluate using the constitutive material. So this is the yield stress value, modulus of steel, and hardening coefficient value that I am creating here. And here I am creating one steel 01 object. Object in the sense here steel 01 is basically a class. So when we have a class, we can create an objects corresponding to that class. That's what I'm doing here. I have created one test material object that corresponds to steel 01 class, and this test material takes these arguments: yield stress, modulus of elasticity, and the strain hardening coefficients. So if you look at these three arguments, what are these three arguments? These three arguments are these three: Fy, E0 and B, and remaining parameters A1, A2, A3 and A4, they are initialized here. So you can give these values, no problem, but they are optional since we have already given some default values for them. If you want to change these default values, you can definitely change it by appending more parameters to this list, 4 more parameters to this list. For now, I'm not going to change them, so I'm just using them. So here I have created a small variable called trial strain. So in this for loop, it takes one value from this strain history and stores it in this trial strain, and then we evaluate the stress corresponding to this trial strain. And for evaluating that stress, we are calling this function set trial strain, that is also defined here, this one. So we are calling this function. This function takes two arguments. One is the strain and the other one is the strain rate. If you look at the strain rate is defaulted to 0.0. So you can give your argument. You can define this strain rate in your source code. Even if you do not define also, it will take this 0.0 as the default. If you define something else for the strain rate, it will take that something else. And then to evaluate the stress, you have to use this get stress function of this steel CPP. Likewise, you can get many properties like a get tangent, you can get tangent, you can get initial tangent, but these are slightly irrelevant for this particular example tutorial. So currently we are focusing on the stress only. So I'm just saving that stress value here. After that, I'm calling this commit state function. Let's see what this commit state function is doing. So if I go to this commit state function, what this function is doing is it is saving certain variables. So what we are doing is in this cyclic simulation process, this process basically is a history dependent process. Means at every step you need the information of obtained in the previous converged steps. That's what we are doing here. Whenever we found a converged step, we save certain variables of that converged step into the database for usage in the next step. That's what we are doing. So the current step, we are calling it as a trial step. Whenever it is converged, we will save those variables into the so-called converged state variables. They are identified with C. T represents trial, C represents converged. Yeah, we are saving this thing, and these parameters we are going to use in the next step. So that's what we are doing here. So after that, we are the stress value that is obtained, we are storing it in this stress history. That's it. We will repeat this for loop for all the values in this strain history. That's it. After that, I'm doing some operations like I'm saving this strain history and stress history into another matrix called strain stress data. So this matrix we are going to save in a separate CSV file. So train stress data s01.csv. If you look at here, that variable, that file is not available currently because it is, we have not run this program yet. So if we build this program and rerun this, we get that file. If you open this one, see, we have got all the stress values corresponding to this strain values. Let's open these things in Python. Let's plot the stress strain curve data. For that, I have created a small function called plot data s01.py. We are going to open this. I'm doing a lot of trial and errors for preparing this tutorial. So I have written all these functions upfront actually, just I am demonstrating them in this tutorial. So this is the small function that we have written. So here we are loading that strain stress data s01.cvv into this Python file and we are plotting it. Just run it. See, this is the stress strain plot that corresponds to the given strain history. If you look at the value of strain history, just change these variables, strain history, plot 1, and let's don't use this. And if I rerun this, you will see this is the strain history that I supplied to the steel 01 material. So for this strain history, let's see what is the stress history that we have got. Just changing these numbers. Stress, let's change the color to blue. Let's rerun this again. So if you see for this strain history, this is the stress history that we have got. Let's change this plot size also to 100. See, for this strain history, this is the stress history that we have obtained. When I plot these two with I'm making some miscellaneous changes, just don't bother about these things. Just for visualization purpose, I am adding appropriate X labels and Y labels. So if you plot it here, for this strain history, we have got this stress history. When we plot the stress strain plot with strain on x-axis and stress on y-axis, we have got this plot. This is the stress strain plot for this given strain history. This is how we extract the CPP files from the OpenSees source code and compile them independently. For example, the main advantage of following this process is, for example, if you want to study how a particular stress value is evaluated for a given strain, what you can do is you just have to put a breakpoint on this set strain function and run your local debugger up to that point, and then you can go into this step function. And if you look at here, what we are doing is we are getting the previously defined converged state values into this trial state values, and we are evaluating this strain parameter called T strain. At this stage, we don't know what is this G strain, but in our future tutorials, we will try to understand what these things are doing, and then we are calling it as if the absolute value of this G strain is greater than dBl epsilon, then we are setting that strain to T strain. So for now, our D strain is very less than the epsilon value. So we are setting T strain to this strain value, and then we are calling another function called determine trial state, and we are sending this D strain to this. So let's see, let's go into it. For going into this, you need to press this button, and then when we enter into this, see, this is what OpenSees source code is very well written. It's beautiful, well architected. Sometime in your academic career, try to explore this source code. It will definitely add value to your career. There is no doubt about it. This is how we are evaluating this ESH value. I don't know what is it, but maybe in coming tutorials we will see what is those variables are doing actually. And then we are evaluating some intermediate variables, and then we are evaluating this a variable called T stress. This is the trial stress that we are getting from this function, and after that we are evaluating some tangent values. So currently we are not interested in them, and then we are doing some other operations, and then we came out of it. After that, we are saving that trial stress that we have got from this get stress function into this stress, and then we are using this commit state function. Let's go what we are doing. So if we look at the trial strain values under the load path definitions, we are saving it into the history variables, these things, t strain, previous values, t stress that we have got, because these values are very important in evaluating the stress at the next point, the coming point. So that's it. This is the main advantage of this particular tutorial actually. So you can actually go into the source code and look at what equations are used within the source code, and you can write them manually, because many a times the actual implementation within the source code and the implementation that we get in the documentation will slightly differ. For example, sometimes in some constitutive relationship, we have to use curves, mainly quadratic curves, to represent the envelopes in the constitutive relationships. But defining those curves in the computer program is sometimes difficult. So people will do some slight changes. They idealize that curve into some series of straight lines. And this kind of little details we get to know in the source code only, because some people will document it very clearly and sometimes people may not document it, and sometimes even if the people document it, we may not go into that detail in the documentation. But if you look into the source code, you don't have any other way. You have to go into that detail to get the exact equation that is used in evaluating the stress. This is how TL01 works. Let's see how Concrete 01 and other things are working. So I have previously written them, so just I am copying them here, and I'll see in Excel material models. So I have written separate files for Concrete 01 and Concrete 02, and then I'm just copying them. These files we will get from the source code, no problem, and I'm just copying this Python files also. So just copying them into the current project. So in this source code, let's add the C++ and header files that we just copied. Let's add these two. Let's add these two, and we missed one more file, that is, yeah. So let's add all these things to the present project, and we have to make sure like here we can only call one main function for a particular project. So since I have already written main here, I'm just calling it as a main yes. So right now this is a function with name main yes, it's not the main function. And let's see, I'm calling it Concrete01 as the main function now, and here I have to make some slight changes, because in my previous trials I'm using an older version of Armadillo library. The latest version is not compatible with the code, so to accommodate the latest version I have made some slight changes. So let's give me a moment. Yes, now it will work. We have to make this main C as main function. Yes, let's run this. It's failed. So why it's failed? So we have got one Armadillo function where, so we have got that error here. So I need to change that in this line as well. These are some cosmetic changes just to accommodate the latest Armadillo library. Yeah, that's it. Let's build it again. As I said, what rebuild does is it just cleans the previous build and do a build again. So currently we don't have any errors, and let's run this Concrete01 behavior and see it's done. And let's open C01. This is how Concrete01 looks for the given strain variation. Let's see how Concrete02 works. I'm making this main. and running this. And just rerun this. Let's run concrete 02. See, we have got tension in concrete 02. That is what is reported here, right? So in concrete 01, we don't have any tension branches. This is concrete 02. Here in concrete 02, we have a tension branch. Overall, this is the tutorial. In our future tutorials, we will go into each material model in detail, and we will try to extract all the equations that were used in defining a particular constitutive model in each loading and unloading paths, and how each unloading and unloading paths are defined also we will also explore. Stay tuned for our upcoming tutorials, and to get notifications of our all upcoming tutorials, please do subscribe to our channel and click the bell icon for latest notifications. If you have any questions or if you get any errors, please do provide them in the comment section. We are happy to help you out. If you like our content, please hit the like button and subscribe to our channel. Happy learning. Thank you.